Internal Corrosion Direct Assessment Methodology for Liquid Petroleum Pipelines, Techniques to Evaluate and Manage Pipeline Corrosion Risks. Internal Corrosion Direct Assessment, ICDA. Overview, Purpose and Applicability of ICDA. Internal Corrosion Direct Assessment, ICDA, is a structured and systematic methodology developed to assess and manage the threat of internal corrosion in liquid petroleum pipelines when inline inspection (ILI) tools are not feasible or not available. The methodology is formally documented in NACE SP 0208 and is widely recognized by regulators and industry as a valid integrity assessment approach. ICDA focuses on identifying locations where internal corrosion is most likely to occur, rather than attempting to inspect the entire pipeline. This targeted philosophy improves safety and cost efficiency by concentrating resources on the highest risk areas. The primary principle behind ICDA is that internal corrosion in liquid pipelines is driven by the presence of water or other electrolytes that separate from the hydrocarbon stream and accumulate at specific locations, typically low points or areas of reduced flow velocity. By understanding pipeline elevation profiles, flow characteristics, operating conditions and fluid properties, ICDA models can predict where corrosion is most likely to initiate and propagate. ICDA is particularly applicable to pipelines transporting refined products, crude oil, or other liquid hydrocarbons where free water may be intermittently present. The methodology integrates engineering analysis, field inspections and validation activities to ensure predictions are accurate and defensible. When properly applied, ICDA supports integrity management objectives by preventing leaks, protecting the environment and ensuring regulatory compliance. It is not a one-time activity but part of a continuous improvement cycle that evolves as new data becomes available. The purpose of ICDA is to proactively identify and manage internal corrosion threats before they result in pipeline failures. Unlike reactive maintenance approaches, ICDA emphasizes prevention through prediction and validation. It is designed for liquid petroleum pipelines where internal corrosion is a credible threat and where operational or physical constraints limit the use of inline inspection tools such as smart pigs. ICDA is applicable only when certain prerequisites are met. These include stable operating conditions, adequate historical and design data, and a reasonable expectation that corrosion mechanisms are understood and predictable. The methodology assumes that corrosion is driven by water accumulation and that flow modeling can reasonably estimate where such accumulation occurs. Pipelines with highly turbulent, rapidly changing, or poorly documented operations may not be suitable candidates. From a regulatory perspective, ICDA is recognized as an acceptable integrity assessment method when performed in accordance with established standards. Operators must demonstrate technical justification, proper execution, and documented results. When applied correctly, ICDA enables operators to meet integrity management requirements while optimizing inspection costs and minimizing operational disruptions. It also provides a defensible framework for decision-making related to maintenance, mitigation, and reassessment intervals. Objectives of Internal Corrosion Direct Assessment or ICDA, four-step ICDA process. The core objectives of ICDA are centered on safety, reliability, and cost-effective integrity management. One primary objective is to identify locations along a pipeline where internal corrosion is most likely to occur, allowing operators to focus inspection and maintenance activities on those specific areas. This targeted approach significantly reduces unnecessary excavations and inspections while maintaining a high level of confidence in pipeline integrity. Another key objective is risk prioritization. ICDA provides a structured means to rank pipeline segments based on their susceptibility to corrosion, taking into account factors such as flow regime, water content, elevation profile, and operating history. This prioritization supports informed decision-making and ensures that limited resources are allocated where they provide the greatest risk reduction. ICDA also aims to support regulatory compliance and continuous improvement. By documenting assumptions, models, inspection results, and mitigation actions, operators create a traceable and auditable integrity management process. Over time, feedback from direct examinations and operational data is used to refine models and improve predictive accuracy. Ultimately, ICDA seeks to extend pipeline service life, prevent releases, protect people and the environment, and optimize long-term operational costs. The ICDA methodology is structured around four distinct but interrelated steps: pre-assessment, indirect inspection, direct examination, and post-assessment. Each step builds upon the previous one, forming a logical and defensible workflow for internal corrosion evaluation. Pre-assessment focuses on data collection and feasibility evaluation. Operators gather design, operational and historical data to determine whether ICDA is appropriate for the pipeline segment under consideration. This step establishes the technical foundation for all subsequent activities. Indirect inspection involves analytical modeling to predict locations where internal corrosion is most likely. Using elevation profiles, flow characteristics, and fluid properties, engineers identify low points and other areas prone to water accumulation. These locations are ranked based on relative corrosion likelihood. Direct examination consists of field validation through targeted excavations and non-destructive testing. Selected sites are inspected to confirm the presence or absence of corrosion and to measure its severity. Finally, post-assessment evaluates the effectiveness of the ICDA process. Results are reviewed to validate assumptions, update models, determine mitigation actions, and establish reassessment intervals. This structured approach ensures technical rigor, transparency, and continuous improvement. Detailed ICDA steps: pre-assessment, indirect inspection, direct examination, post-assessment. Pre-assessment is the foundation of the ICDA methodology and determines whether ICDA can be reliably applied to a given pipeline segment. During this step, operators collect and review all relevant data, including pipeline design information, alignment sheets, elevation profiles, operating pressures and temperatures, flow rates, product composition, and historical corrosion or failure data. A critical element of pre-assessment is evaluating the potential for electrolyte formation. This involves understanding water content in the transported product, sources of water ingress, and operating conditions that may allow water to separate from the hydrocarbon stream. Without credible water presence, internal corrosion is unlikely, and ICDA may not be justified. The pipeline is then divided into ICDA regions based on changes in diameter, elevation, flow characteristics, or operating conditions. These regions form the basis for subsequent modeling. Data quality and completeness are also assessed, as inaccurate or missing data can undermine the entire ICDA process. If significant data gaps exist, they must be addressed before proceeding. Successful pre-assessment ensures that ICDA is technically valid, defensible, and likely to produce meaningful results. Indirect inspection is the analytical phase of ICDA, where modeling techniques are used to predict internal corrosion susceptibility along the pipeline. The primary objective is to identify locations where water is most likely to accumulate and persist, creating conditions conducive to corrosion. Using elevation profiles and flow modeling, engineers identify low points, sag locations, and areas of reduced velocity where water dropout may occur. Hydraulic models may be applied to simulate flow behavior under various operating scenarios, including normal, reduced, and transient conditions. These models help estimate water holdup and residence time. Each identified location is then ranked based on relative likelihood of corrosion, considering factors such as water availability, flow regime, temperature, and known corrosivity of the product. The output of indirect inspection is a prioritized list of candidate sites for field validation. The accuracy of this step is critical, as it directly influences where excavations and inspections will occur. Conservative assumptions are often used to ensure that high-risk locations are not overlooked. Direct examination provides field validation of the predictions made during indirect inspection. In this step, a selected number of high-priority locations are excavated and inspected to confirm the presence, type, and severity of internal corrosion. Site selection is based on ranking results, accessibility, and safety considerations. Once exposed, non-destructive testing methods such as ultrasonic testing (UT) or radiography are used to measure remaining wall thickness and characterize corrosion features. Visual inspection and internal surface condition assessments may also be performed where possible. Data collected during direct examination is documented in detail to support technical evaluation. The primary purpose of this step is not only to find corrosion but also to validate the predictive model. If corrosion is found where predicted, confidence in the ICDA process increases. If discrepancies are identified, assumptions and models must be re-evaluated. Direct examination results form the factual basis for integrity decisions, including repairs, mitigation, and future assessment intervals. Post-assessment is the final step of the ICDA process and focuses on evaluation, learning, and decision-making. Results from direct examination are analyzed to determine whether the ICDA predictions were accurate and whether corrosion rates and severities are within acceptable limits. During this step, operators assess the effectiveness of the models and assumptions used during indirect inspection. If necessary, models are refined to better reflect actual pipeline behavior. Mitigation actions are then identified and implemented. These may include enhanced pigging programs, chemical inhibition, operational changes, or repairs to damaged sections. Post-assessment also establishes reassessment intervals based on observed corrosion rates, confidence in the ICDA process, and regulatory requirements. Documentation is critical, as this step provides evidence of due diligence and continuous improvement. A well-executed post-assessment ensures that ICDA remains a living process, adapting to new data and changing operating conditions while maintaining pipeline integrity over time.